Sorry for the delay. So before we begin, like a couple of quick announcements. So the first assignment is due next week, right? So how is it going? So you will have a full office hours about the tomorrow's office hour is going to be for A1. So just please don't talk in this. If you have any questions about the first assignment, you can use tomorrow's office hour to talk to the TA. Audio? Yeah, I think this mic is. Check. Is it better? No. This is not a good mic. Um, check. See. Okay. Is it okay or? Okay, I might need to hold it like they have two mics for this auditorium. This is the bad mic. Okay, so assignment 1 is due next week, and if you have any questions still, like you can use the office hours tomorrow to talk to the TA responsible for assignment 1. Okay, as I mentioned before, aim to submit the assignment at least a couple of days in advance. Like don't wait until the last minute. A2 will be released next week, I guess. And about the midterm. So I think the schedule already says that. So the midterm is on 23rd October, right? Is it 23rd? Yeah. So 23rd October, it's actually during the lab time. Okay. So the exam is from 5 p.m. to 6:30 p.m. So be there at least 15 minutes in advance. So we're going to have a couple of rooms for the midterm. So when it is close to the time, like, so we will tell you which room you belong to, like, so that you can go to the respective room. Is that clear? And the syllabus for the midterm is going to be the first 7 weeks. And you, after 7 weeks, you have a study break or fall break. So followed by an 8th lecture before the midterm, but that's not included in the midterm. Yeah. So everything that we do in the first 7 weeks, including whatever you see in the lab, is considered for the midterm. And typically, I allow a cheat sheet for the finals, but not for the midterm. So midterm is completely closed book. Okay, so you cannot bring anything to the exam. This is also to make sure that you study your fundamentals as long as you can. Like so, but for the finals, I will allow you to bring an A4 sheet. Is that clear? But for the midterm, there is no cheat sheets. We are already at 4th week, so that's more than half of the syllabus. So if you have not started preparing for your midterm, like I encourage you to catch up on whatever we have seen so far. Like so the recordings for all the previous lectures are available in the schedule. Like so um, if you want to go back and rewatch some lectures, you can do that. Okay. And I have also released the last 2 years midterm papers in this. Like if you go to the schedule now, well, I did it yesterday. So if you go to the schedule now, like you can see a link for the previous 2 midterm exams. Okay. So I decided to release both the previous midterms so that I can challenge myself to set up a completely new midterm. So like don't overfit to the questions in the midterm papers. Okay, so these are samples from last year's. Like it's not going to be exactly similar for this year. Like so, like you could get different kinds of questions. So that doesn't. the last two midterms. Is that clear? Any questions before we begin? Okay, so let's get started. But this is not very convenient for me. So I'm going to try once. Okay, so I'll try to speak louder, but this is fine, right? Okay, for now this works. Okay, okay. So let's get started. So what did we do last week? Gradient descent. We did gradient descent, like so, which is basically an iterative algorithm for finding minimum of a function, right? Like so, if you cannot find a minimum using closed form solutions, then you can use the idea of computing the gradient, which shows you the opposite direction, right? Like the steepest direction. You take the negative of the gradient to move, but then you don't want to make a very big step, so you do minus alpha times gradient, where alpha is the learning rate or the step size, right? And we talked about different variants of gradient descent. So can someone tell me what are the three variants of gradient descent discussed last week? Stochastic gradient descent. So what is stochastic gradient descent? So you update the weights for each data point. That is stochastic gradient descent. Like what are the other two variants? Mini batch. So full batch gradient descent and mini batch gradient descent, right? Like so full batch gradient descent means you're using all the examples to compute the gradient. And mini batch is something in between stochastic and full batch. Like so you take a mini batch of examples, like k examples, which but k is typically much lesser than the total batch, like the total data set size, right? Like and you do a gradient update just with this mini batch, right? And typically when people say they're doing gradient descent, it is mini batch gradient descent. Like so, like nobody does full batch gradient descent anymore because the data sets are so huge, and also nobody does completely like extreme, like one example gradient descent just because it's not efficient for hardware. Okay, so people do mini batch gradient descent. And towards the end, I think we also discussed the idea of regularization. We talked about L2 regularization and L1 regularization, right? So that's where we start. Okay, so as I mentioned in the last week, like so today's class is more on the foundations of the prediction problem itself. Okay, so we're going to start with statistical decision theory. I'm going to do this for regression, but once we start seeing classification algorithms, we will redo this for classification. Okay, so for today, we will focus on regression because we have seen regression enough, right? So let's say I have some input x, which is p-dimensional. Okay, so I have p features. Okay, now this is a real value random input vector. Okay, and my y is a scalar. Okay, so it's a real value random output variable. Okay, so for today's lecture, we are going to take a probabilistic view of what is happening when we are trying to learn a model. Okay, so for the last few lectures, like we did not talk about probabilities, right? Like so now I'm going to assume that x is a random input vector, okay, and y is some random output variable, okay, and we're going to consider the joint distribution of x comma y, okay, which is represented as probability of x comma y, so it is the joint distribution of x comma y, okay. So we're going to assume that there is some joint distribution from which your data set is sampled. So you sample x comma y from this joint distribution like multiple times. Let's say you sample it 100 times. you're going to get a data set of 100 x comma y pairs. Is that clear? Okay. Now, the goal of regression is to find a function f of x, right, for predicting y given values of x, right? So that is the goal. Like, so we are interested in finding some function f of x for predicting y given x, right? And typically we will have some loss function. I'm going to represent the loss function as L of y comma f of x, okay, which is basically the loss function for penalizing errors in the prediction, okay? So the loss function that we have seen so far in this course is the squared error loss, right? So the squared error loss L of y comma f of x is given by y minus f of x the whole square, okay? So you have a 1 over 2, but that doesn't matter here for this discussion. Is that clear? Okay. For now, I'm talking in abstract sense, in the sense I don't know what is f of x, right? Like, so in linear regression, f of x is w0 plus w1x or w transpose x in general, right? But for today's discussion, it doesn't matter what my function is, okay? So we are interested in thinking about this question, like, so what is an ideal function that would make the best prediction that is possible, okay? So then we can worry about whether it is W transpose X or something else, okay? So to find the ideal function, like, we are going to compute the expected prediction error, and we are going to minimize this expected prediction error, okay? So the expected prediction error of any function f is given by the expected value of the loss function, which is y minus f of x the whole square, okay? Now, this expectation is over both x and y, right? Like, so we are talking about the joint distribution of x comma y, right? So this is an expectation over x and y. So we are assuming that x and y are continuous random variables. Like, so it's going to be double integral y minus f of x the whole square, probability of x comma y times dx dy. Okay? So I can write this as integral over x, integral over y minus f of x the whole square, p of y given x dy, p of x dx, right? So, well, I skipped a step here, but if you want me to write that step by step, like, so first I can factorize p of x comma y as p of y given x times p of x, right? So then I'm just moving dx and dy around. So this becomes integral over x, integral over y minus f of x the whole square, p of y given x dy times p of x dx. Okay. Now, what is this term? What is this term? So integral over y minus f of x the whole square, p of y given x dy. So what's this term? Yeah. It's just a conditional expectation of y minus f of x the whole square, right? It's just a definition of expectation, actually. So this is actually integral over x, the expected value of, okay, so this is expectation over y given x, y minus f the whole square given x is equal to x times p of x dx, right? Now, what is this expectation? Sorry, well, I told you this is an expectation. So what is this term? This is also an expectation, right? So this is just integral x something p of x dx. It's an expectation over x. So I can write this as expectation over x, expectation over y given x, y minus f the whole square given x is equal to x. So this is my expected prediction error for a function f. Okay. Now I want to minimize this expected prediction error, right? Like, so the ideal function approximator for the regression problem is given by argmin of f, okay, expected prediction error of f. Is that clear? Okay. Now you look at the expected prediction error. So x is given typically, right? So which means if I minimize my expected prediction error point-wise for all possible x, then I would get the minimum expected prediction error, right? So I can do this as argmin f, simply e of y given x, y minus f whole square given x is equal to x. Okay. So what we are going to do now is to differentiate this function, set it to 0. That's going to give us our f star. Okay. So I'm going to do dou by dou f of, sorry, of expected value of y given x, y minus f the whole square given x is equal to x. And I'm going to set this to 0. Is that clear? Yeah. Because typically we don't have control over x. X is given to us. Okay. So we are basically trying to minimize this pointwise for all x. So I'm going to copy this to the next page. Okay. So let's try to do this differentiation. Okay. So we are interested in doing dou by dou f of expected value of y minus f the whole square. This is a minus b the whole square. So I'm going to expand this. So you will get expected value of y square given x is equal to x plus f square minus 2 times e of y given x, y given x is equal to x times f, the whole thing is equal to 0. Okay. So can someone tell me why I don't have the expectation for f square? So I'm doing a minus b the whole square. So it's a square plus b square plus 2ab, right? So why don't we have the expectation for f square? Sorry? Yeah. It doesn't depend on the y. Okay, so it's not a constant, it's a function, right? Like, however, this function is not dependent on y. So it's independent of y, which is why here also you have e of y given x, y given x is equal to x times f. Okay? Okay, so we will differentiate this. So what would be the differentiation of the first term with respect to f? 0, because there is no f, right? Like the first term is not a function of f. So when I differentiate this term, I'm going to get 0 plus, what is the differentiation of the second term with respect to f? 2f, okay. What about the third term? So minus 2 e of y given x, y given x is equal to x, right? So the whole thing equal to 0. So which means my f star is expected value of y given x is equal to x. Okay. So what this derivation tells us is this is the best possible f for least square error. Okay. Now, this is much more abstract than what we have seen in the previous classes. Okay, so I'm still not talking about what is f, right? Like, so what is the parameterization of f? Like, all I'm saying is, if you want to solve least squares, the best possible solution is simply the conditional mean of y given x. Okay, if you think about it, it is very intuitive. Like, so if x and y come from some probability distribution, and I ask you what is y given x, because it is stochastic, the best possible answer is just the mean of the conditional mean of y given x is equal to x. Is that clear? Any questions? Okay, so this is the best thing that we could do, right? So now let's go back and think about the two algorithms that we learned for regression, the nearest neighbor regressor and linear regression, and see how they try to approximate this best solutions. Okay, so we're going to start with nearest neighbors. Okay, so just for comparison, like I'm going to put f star here. F star is basically e of y given x, y given x is equal to x. This is the ideal function approximator, right? Now, what does nearest neighbor do? So nearest neighbor is making some prediction, which is basically average of yi given xi belongs to the neighborhood, right? This is roughly what nearest neighbors regression is doing, right? Like nearest neighbor regression, it actually finds some neighbors of x and takes an average of yi given like yi of these neighbors, right? Now, let's try to compare this function and this function, okay? If you watch closely, nearest neighbor is doing two main approximations, okay? So the first approximation is the expectation is approximated by averaging over sample data. Okay, instead of taking expectation, nearest neighbor is taking an average, which is a good approximation of expectation over the sample data. Okay, and the second approximation is instead of conditioning exactly at x, nearest neighbor is approximating that conditioning by looking at the neighbors. Okay, so conditioning at a point is relaxed to conditioning on some region, okay, that is close to x. Is that clear? So these are the approximations of nearest neighbor. So remember that in real life, you will never be able to compute this E of y given x. Why? Because we don't have access to the joint distribution, P of x comma y. Okay? For any real problem, we don't have access to the true joint distribution P of x comma y. If you have access to that, then you can just compute this f star yourself. Okay? Because we don't have access to the joint distribution, we are trying to make some approximations, right? Every machine learning algorithm that you are going to learn is going to make some approximation for this f star, okay? And the approximation that nearest neighbor is making is this. Like, so instead of, I know I should do E of y given x is equal to x, right? But I'm going to approximate that by considering the neighbors and taking the average of the neighbors. Is that clear? So now I can actually show that as n and k tends to infinity, what does this mean? This means that I have infinite number of data points. So n tends to infinity. The neighborhood also tends to infinity, okay, such that k by n tends to 0. So this means n reaches infinity faster than k. Okay? So then I can actually show that the nearest neighbor solution actually tends to E of y given x is equal to x. Okay. So with lots and lots of examples, like so with infinite number of examples, and also the number of neighbors being too huge, right? This statement says that nearest neighbor is going to be at the limit equal to S star. Is that clear? So if you have enough examples, nearest neighbor is a great approximation, sometimes reaching the performance of F star. Okay, so which is why people often call nearest neighbors as universal function approximator. Is that clear? It looks like we have a great algorithm, right? Like, so then why do we need other algorithms? Like, so like if nearest neighbor can approximate F star as close as possible or even reach the performance of F star, then we don't need fancy machine learning algorithms, right? Now, so here is the bad news for nearest neighbor. Even though it looks like a very powerful algorithm, so the catch here is you need lots and lots of examples. Okay. Now, the number of examples required just grows exponentially as the problem complexity grows. Okay. So, in other words, as the number of features increases, when you have high dimensional problems like 100 features, 1,000 features, million features, right? So, we need very, very large samples. Okay. At very high dimensions, the number of samples required to compute meaningful average, right? That grows exponentially. Like you will not get the data. There is no way you will get enough data to have a good nearest neighbor approximation. Okay, I'm going to show that through an example. But is the idea clear? So this idea that at high dimension, nearest neighbor breaks or things just gets much harder, right? Like so this is famously called as the curse of dimensionality. Okay, first popularized or like proved by Bellman, 1961. Okay, so he did this in the context of dynamic programming, but the curse of dimensionality shows up everywhere. Okay, so let's try to understand what we mean by curse of dimensionality, right? So to do this, I'm going to consider a p-dimensional hypercube. Okay, so for visualization, I'm doing a 3D hypercube here. Okay, so this is a 3D hypercube, but consider a p-dimensional hypercube. Okay, now this is a unit length hypercube, which means so the length in each dimension is normalized between 0 to 1. So every dimension is 0 to 1. Okay, and I'm going to consider a small neighborhood, which is this blue color, right? So this is my neighborhood. Okay, now let's say I'm interested in finding the expected length that I should cover to get R fraction of observation. Okay, like I want to get R fraction of my observations as my neighbors. Okay, so how long should I go in the line to do this? Okay, so this is basically the inverse of like you can compute the volume of this small blue color thing, and from that you could compute the expected. Like if the volume is R, right? Like what would be the expected length? So I'm saying that the volume of this blue color cube is R. So what would be the expected length of sides? Sorry? Yeah, it's cubic root, right? Like, so in general, if it is a p-dimensional hypercube, then the expected edge length is given by r power 1 by p, right? So let's just call this as EP of r, which is r power 1 by p. Now, if you do some calculations, when you have 10 features, okay, so the expected prediction length to cover 1% of example, just 1%, okay, is 0.63. And if you want to cover 10%, that is 0.8. Okay, so here I'm plotting the fraction of volume that you could cover by reaching the distance. Okay, as you can see, when you have only one feature, things look fine, right? When you have even just 10 features, to consider 20% of the data as your neighbor, okay, you need to cover almost 0.85 out of 1 in the space. At this scale, nearest neighbor is not a nearest neighbor anymore, right? Like, so, like when you're really covering the whole cube just to get 20% of the neighbors, right? It's not a good approximation anymore. Like, so you are really considering the whole data set and you're taking average over the whole data set. Is that clear? Yeah. Okay. So what this says is, if you want to cover 0.2 fraction of the volume, okay, then in the cube, right, like in the cube that you have, for 10 dimensions, you need to go all the way up to 80%. So you need to cover the 80% of the feature range. Okay, so this is simply not possible when you have 1,000 features. Like when you have 1,000 features, like you need way too many examples to have a more reliable approximation. Is that clear? So this is the problem with high dimensional features and nearest neighbors. Okay, now this is the problem that any traditional textbook talks about, especially books that are written by statisticians, right? Like we're doing statistical decision theory. But from the practical machine learning perspective, nearest neighbor is not such a bad algorithm. Okay, so it is not, this figure is not completely true. Okay, so yes, you need lots and lots of examples, like when you're in high dimensions, okay? But this kind of misses the fact that even though we deal with a lot of high dimensional data, the problems that we deal with are almost always low dimensional. Okay, let me give you an example. Let's say we work with images, like I want to do image classification, okay? And I have an image which is 1024 cross 1024 pixels, and with RGB, three channels, it becomes 1024 cross 1024 cross 3, right? So this is the number of pixels I have, so which is basically the number of features I have. This is way too many features, right? Now, if we go by this logic, nearest neighbor should not work at all, right? Like, because to do nearest neighbor with k is equal to 10, it doesn't make sense. With 10 examples, like you're not going to cover any meaningful portion of the data, so your nearest neighbor should not work. But when you try implementing this, I'm hoping that you would do this in your second assignment, but I haven't seen the second assignment yet, so I will verify. But when you do this in practice, you will realize that nearest neighbor is not such a bad algorithm. It will actually do well. Like it's quite a good baseline when compared to other methods. Okay, can someone reason why? So why does it work when I have such a large number of features? I'm doing image classification, and my features are 1024 cross 1024 cross 3. Okay, and I'm doing nearest neighbor with k is equal to 10. it works. So the question to think about is, why does it work? Yeah.
There's not that many classes, so the nearest neighbor is.
Oh no, it's not about the classes. Like, so it doesn't matter how many classes you have. Yeah. Let's take this example. Like, so when I do image classification, like so. Okay. That's not what I'm looking for. We can think about it, but are there any other answers? Okay, so think about this. Even though this looks like a high dimensional problem, like because you have 1,000 times 1,000 features, right? It's not that high dimensional problem when you consider the fact that you can consider all permutations of these pixels. You will notice quickly that there is a very small fraction of that are actual images. Okay, you cannot try different pixel values like and create a useful image. Okay, so maybe 99% of the combinations is not going to be any meaningful picture. So the actual data that you care about, which are basically the pictures, right? They lie in a low dimensional manifold in this high dimensional space. Even though the space is high dimensional, the data lies in a low dimensional manifold. The k nearest neighbor can still work. Is that clear? So I think this is a point that many of these textbooks miss, mostly because they are written by people coming from statistical background. Okay, so all I'm trying to say is like k nearest neighbor is not such a bad algorithm. Okay, so you should try whenever you want a good baseline. Okay, so now let's talk about linear regression. Okay, so I'm gonna rewrite the f star here for reference. So f star is expected value of y given x, y given x is equal to x, right? This is just for reference. So the linear regression is given by simply w transpose x or x transpose w, whatever way you want to write it. Right? Now, how is this approximating f star? So how is this approximating f star? So what kind of assumptions that linear regression make about f star? It's not very clear, right? So one thing I can say is linear regression is actually taking a model-based approach. Right? Which means linear regression makes an assumption that f star looks like a line. It's making the linearity assumption, okay? It is making an assumption that f star looks like a line, and it is learning the parameters of this line from the data. Is that clear? Is this a good assumption to make? It's hard to guess. We don't know how the true function looks like, right? If the true function is a line, the linear regression is probably the best possible prediction algorithm that you could think of, right? But this is where the problem with model-based approaches come in, okay? So when you start making assumptions about the model, saying, okay, my model is W transpose X, or my model is a polynomial function, right? So when you start making these assumptions, these are irrecoverable assumptions. Like, so what do I mean by that? Like, so once you make this assumption and start training a model, you are limited. Like, so once you start making this assumption that your model is linear, you will never find a solution that is outside the space, right? In some sense, whenever you do model-based machine learning, you are restricting the class of functions that you could search for, F star, and you will find whatever is the best possible F approximation in this restricted class. So is that clear? So this has some implications. We're going to talk about it in detail today. Yeah.
My question was, if the linear regression assume that it's the solution is linear, what does it mean about the variance? Does it mean like it has a low variance?
Yeah, we'll talk about it. So we will talk about it after the break, okay? So now I want to highlight the assumptions made by these two algorithms, okay? So linear regression makes this assumption that f of x is well approximated by a globally linear function. This is a very strong assumption, okay? Now, what is the assumption for k nearest neighbor? I think we saw this towards the end of the last lecture. So k nearest neighbor makes this assumption that f of x is well approximated by a locally constant function. Okay, it assumes that locally things are constant. Like locally, in a neighborhood, the prediction is same, right? It is just the average, right? So each algorithm that we are going to see in this class is going to make one such core assumption. Okay, we're going to call this core assumption of an algorithm as inductive bias of the algorithm. Okay. Typically, you have to make some assumptions to learn. You cannot learn without any assumptions. The problem is just too hard, okay? Because I'm telling you that there is a joint distribution of x comma y, which is generating x and y. I'm asking you to find y given x, okay? Because the problem is high dimensional, we will discuss this in detail in the future classes, okay? So because the problem is high dimensional, it's just not easy to come up with an algorithm which doesn't make any assumption and still attempt to do the best possible prediction, okay? So we often call this as no free lunch theorem, okay? So no free lunch theorem just means there are many variants of no free lunch theorem. Like the variant that is useful for today's lecture is there's no free lunch, which means you cannot come up with an algorithm which doesn't have any assumptions, okay? So you have to make some assumption, okay? Now, the moment you start making assumptions, you're locked with those assumptions, which means it is not an universal algorithm anymore, right? This algorithm will work only when that assumption is true. When the assumption is false, your performance is going to be bad. So this is another way to say that it is extremely hard or almost impossible to come up with what some people call as the master algorithm. Okay, like so it's impossible to come up with one algorithm that works for every setting. So we need to make assumptions. And part of being a good machine learning researcher is to understand what assumptions to make in what situations. Okay, so we will talk about this in detail, like for every algorithm that we're going to see in this course. Like, but roughly, for now, what is important is you understand that every algorithm makes a core assumption, and we're going to call this the inductive bias of algorithm. Okay, and the inductive bias for linear regression is the function is globally linear, right? And the inductive bias for k-nearest neighbor is the function is locally constant. Is that clear? Okay, so typically your algorithm, okay, I'm going to define three important components of the algorithm. Like, so one is the parameters that we are learning from the data, right? And algorithms also come with hyperparameters, which are not learned from data, but picked through model selection with the validation set, right? And they also have inductive bias, which is the core assumption that the algorithm makes. Is that clear? Okay, so far we looked at L2 laws, right? So you should, okay, the most important thing to recognize is this is an ideal function approximator for least square error, not for the whole regression. Okay, so this is not the best F star for the regression problem itself. This is the best problem for regression when you're trying to minimize least square error. Okay, so which means you could ask, oh, what if I change my loss function, right? So far we were doing regression only with L2 loss, right? But you could also do regression with L1 loss. Okay, when I'm doing regression with L1 loss, I'm trying to minimize expected absolute value of y minus f of x. Okay, so to compare this with L2 loss, so the L2 loss is given by expected value of y minus f of x, the whole square. Okay, so we derived that f star when you are doing L2 loss is basically the mean, conditional mean of, well, I can just write it as mean of y given, then that's the conditional mean. So it's basically the mean of y given x is equal to x, right? You can do a similar derivation for L1 loss. Okay, I don't think that that's the focus of this lecture. Can you guess what would be the ideal F star when you do L1 loss instead of L2 loss? Yeah, it's going to be the median, okay, of y given x. So the F star here is the median of y given x is equal to x. Okay, so in general, you can come up with new loss functions and you do the whole minimization of expected prediction error, you can find what is the ideal F star. Okay, so for regression, people most often use L2 loss. You can see people using L1 loss sometimes. Okay, there's also another loss called Huber loss. Okay, which is a combination of L2 and L1. It acts like L2 until you are closer, and then it acts like L1. Okay, so well, I'm not writing the function here, like, but you can go check. Like, so this is another way to define loss function for regression. Is that clear? Any questions so far? Yeah. Oh, for L2 we derived it, right? So if you do the same derivation for L1, you're going to get median. Any other question? Okay, so we'll stop here, take a 10-minute break, and then we'll continue the discussion.